Welcome to this video lecture on the normal distribution. The normal distribution describes variables from a great number of different scenarios, such as measurements that arise in nature, or dimensions that arise during manufacturing, or the types of errors that occur when measurements are made. In every one of these situations, the distribution is described by two parameters: mu, the mean, which tells you typically how big the numbers are, and sigma, the standard deviation, which tells you how widely spread about the mean the numbers are. The shape of the distribution has this characteristic bell shape, which bulges up in the middle with a single common value, a mode, and then which tails off on either side in a symmetric way to the left and to the right, representing the lower values and the higher values, which get increasingly rare as you move away from the mean in the centre. The way we deal with a normal distribution when we want to calculate probability is we calculate a Z-score. Now, Z represents where a number belongs in its particular normal distribution. So the normal distribution will have a mean and standard deviation that are known, and then we have some value x that is of interest to us. So we calculate how far is x above the mean, x minus mu, and we express that in standard deviations by dividing by sigma. So the Z-score means how far above the mean is this value in standard deviations. Of course, Z can be a negative value when the value of interest is below the mean. So Z, the standard normal score, allows us then to associate a probability with any value that might arise. Here's our first example. Let's say that the heights of men are normally distributed, with mean mu 175 centimeters and standard deviation sigma of 10 centimeters. Suppose we want to know what is the proportion of men that are taller than 182.5 centimeters. Then we proceed as follows. We substitute the values for x, mu and sigma into the formula for Z, and we find that 182.5 corresponds to a Z-score of 0.75. This means the value we're talking about is a little higher than the mean. 0.75, it's plus 0.75, so it's above the mean or on the right of the mean. And 0.75, it's not one full standard deviation above the mean. So we can now draw a sketch where we draw a bell-shaped curve and put a tick mark in the middle at 0, because 0 represents the mean, a value that's neither above nor below the mean, and so 0.75 is to the right of 0. So we mark 0.75 to the right of 0 and draw a vertical line segment, and then because we're interested in the values above that value, we shade the area to the right. So that shaded area is the normal tail that we're interested in calculating the probability of. The area represents the probability. The total area under the curve is 1, and the shaded area represents the probability that a Z-score will be greater than 0.75, which in this case is the same as the probability that a man is taller than 182.5 centimeters. We look at that tail and we can see obviously that it is a minority. It is less than half the total area under the curve. So we know that the probability represented by that area is less than 0.5. It is a minority, not a majority. But to find out the exact value of that probability, we will need to refer to tables. So we refer to tables of the normal distribution, which you can find in the back of the textbook or elsewhere. And on the page dealing with the normal distribution, if we look down the leftmost column, which is headed Z, we look to find 0.75. Well, we can find a 0.7, but to find the second decimal place, we'll have to come across through the columns. So 0.75, 0.7 down the left, and 0.05 up the top. If we come across, we will find that the value involved is 0.7734. So the tables are suggesting that the probability that we require is 0.7734. However, that couldn't be the case, because we're looking for a minority. So obviously the tables has provided us with the majority probability, and the tables will always do this. The tables always provides the majority probability corresponding to a z-score, either positive or negative. And we must then decide, do we require a majority answer or do we require a minority answer? So we subtract the tabulated value from 1 because we want not the majority but the minority. And 1 minus represents not in probability. 1 minus 0.7734 is 0.2266, or as a percentage, 22.66% of men are taller than 182.5 centimetres. So that's how we deal with this first problem, where we have a single value of the variable and we wish to associate with that value a particular probability that describes how often it will be exceeded. Our second example is similar, except that there are two values of interest this time. So again, the heights of men are normally distributed with mean mu equals 175 centimetres and standard deviation sigma equals 10 centimetres. This time we want to know what is the proportion of men that are between 165 and 170 in height. So this time we have two values of x that interest us. x1 is 165 and x2 is 170. We must calculate the corresponding z-score for each of these values of x. So the z1 score is 165 minus 175 over 10, which is minus 1. And the z2 score is 170 minus 175 over 10, which is minus 0.5. On each occasion, we substituted the relevant value of x into the formula. We also substituted mu and sigma to find the z-scores. Now, both of these z-scores are less than 0, they're negative, and of course they should be, because the two values we're dealing with are both below the mean. So when we draw a sketch and represent these values on the sketch, they will both be to the left of 0. So we draw a sketch as before of a bell-shaped curve and put a tick mark at 0 in the middle, and then we are careful to mark the two values, minus 1 and minus 0.5, to the left of 0 to represent the area that we require. So we shade in the area between those two values, and our task now is to find what is the size of that area, because that area represents the probability that a z-score falls between minus 1 and minus 0.5. We have to break this problem down because we can only look up one z-score at a time in the tables. So we will begin this problem by finding out how large is the left tail. That is the white area to the left of the shaded area, which is excluded from it. Then we will look at the right tail, the tail on the right side, which is that larger majority tail. And then we will add those together to get the total tail area, and finally subtract the total from 1 to get the interval area. So we're going to follow these 4 steps. So again, we go to our tables. Our first z-score is minus 1. Now, minus z-scores don't arise in the table. However, minus z-scores and plus z-scores have exactly the same probabilities associated with them because the curve is symmetric about 0. So for z equals minus 1, we find 1 in the tables, and the corresponding probability for z equals 1 is 0.8413. So the tables suggest 0.8413 for our left tail area, and for z2 we have minus 0.5, and the table suggests 0.6915 as the probability corresponding to a z-score of minus 0.5. There's the second page of the tables if it's needed. We don't need it on this occasion. Now, so we lay out the problem like this. Looking at our little sketch, the left tail area, we can see visually, it is obviously a minority. It doesn't get as far as the center of the curve. So it's less than 0.5. So although the tables has suggested an answer of 0.8413, we know that that cannot be the case. So we subtract that number from 1 and we get 0.1587, which is the left tail area in our diagram. Our next job is to find the right tail area, which we can see by inspecting the curve. It's bigger than 0.5. And when the tables suggest 0.6915 as that area, that is a reasonable value for the probability. So we accept that and don't subtract it from 1. We're looking for a majority and the tables has given us a majority. So we just keep that as it is. 0.6915. We then move on to the total tail area. So we add together the left tail area and the right tail area. Adding those two gives us 0.8502. So that's the total area in the tails. That is the total area under the curve that is not included in the interval that we have shown by shading it in the diagram. And so if we subtract the total tail area from 1, we get the area that's not in the two tails, the area of the interval. And that gives us 0.1498 or 14.98%. So this is the probability that a man's height falls between 165 and 170 centimeters. You can read more about this and attempt some problems in the textbook in section 3B.